material stress strain relationship. So first of all, we draw a reinforced concrete member. Draw a reinforced concrete member in this form, which contains a reinforcement. What is the reinforcement? Then when we subject or apply load on this member, apply loads, this member is expected to deflect. I have a shape of this form. This is the deflected shape of this member. I have a deflected shape of this one. Member is expected to have deflected. Based on this, let me draw it. So we have this. Let's call this our initial member. We pick up a shape. Okay. So these are deflected shape. So here we'll have our reinforcement, deflected shape. Then cracks are expected to develop when it deflects. So we'll call this, term these as flexural crack. We term these as flexural cracks. Flexural cracks at collapse. So from this, we go ahead to draw. We're still talking about material stress strain relationship. Material stress strain relationship. So we go ahead and plot the curve. We have a curve from this, which we term as the load deflection curve. Load deflection curve. So these are load deflection curve. Here we have at plastic state. We call this plastic state. We call this at crack or elastic state. We call this at uncrack state. So here we have uncracked. Call this uncracked. We call this cracked or elastic state. Then we'll call this plastic state. Then this is the load. Here we have deflection. That's why we term it load deflection curve. We have plastic, cracked or elastic state. Then we have uncracked state. Then we proceed also with wipe off this. We look at our third diagram, which we term as the effective section and stress distribution. Let's draw it. So we'll start with our section. Is our section. Then here we have, let's dot it. We have a dotted line down here. We have a dotted line here. Then we'll consider the neutral axis at the center. Move it this way. Then here we have, we call this our neutral axis. Neutral axis. Then we'll term this, we have our reinforcement here. So the next thing we draw here is our allowable stress diagram. Draw it this way. Don't mind that my hands are not straight. We'll look at this. What is allowable stress? Allowable stress. Then we also have, we draw the second one, draw the third one, which is called is the ultimate stress. Called is ultimate stress diagram. And this is the ultimate stress diagram. So this, we term this yield stress at collapse. Then here, this is still the allowable stress. The allowable stress. So we could term this our section or effective section. Effective section. Then we shed this side. So this is what we have. So we'll term this as effective section and stress distribution. That's this diagram, which is C. Effective section and stress distribution. Distributions, that's what we have here. So at this point, this is the effective section, while this represents the effective load. While this represents plastic at collapse. This is plastic at collapse. So these are the three diagrams we have here: effective section, effective load, then plastic at collapse. Then the next thing we need to look at under material stress strain relationship. We still need to look at the short-term design stress strain curve for normal weight concrete. Short-term design stress slash strain curve for concrete, for normal weight concrete. So that's what we need to consider. We draw that. We can use tools to draw that in order not to make it too curvy. This is our curve. Okay, draw another one here to make it better, then so that we can make it neat. Then we'll have this. Then here we term this. Here we also go ahead. We can use freehand to do this. Draw our curve from here. So we go this way. So here we can use this to interpolate. Here we trace this passing through here, our dotted line. So we'll pick this down, make this neat. So drop this down. Then this very one, I have this also. We should term this. This is called is the parabolic curve. This is our parabolic curve. From the stress strain curve. Then we have this strain here. This is strain values. Then we term this is stress values, and this stress or compressive stress. This one here, where this value corresponding to this is 0.67 FCU, 0.67 FCU over mean strength or the material strength. So here we this is our strain value at this point. At this point, we have this our strain value. Then our tangent, we look at our initial tangent of the parabolic curve is given here as 5.5 square root of FCU over the material strength in kilonewton per millimeter square. So based on this stress strain curve, where three features we need to consider are the initial elastic modulus of concrete, which is defined as the initial tangent to the parabolic curve, which is given here. Then another thing we need to consider, second feature we need to consider, because this very one is here, then we have to consider the ultimate stress of the design concrete. For design purpose, the ultimate strength, we consider this ultimate stress, we consider this. Then we also consider the ultimate strength for concrete design purpose, we consider this very one here. So these are the three major components of this short-term design stress strain curve for normal weight concrete. Then the next thing we have to consider is the curve for steel. So short-term design stress strain curve for steel, short-term design stress strain curve for steel. So consider this. So we draw the diagram for that. For this, let's pick a line so that we'll make it neat. So consider our first line, our neutral axis, something of this nature. Then we go ahead with our diagram. We have this, we will have this, draw this, then we'll draw it this way. We have something of this nature. So we'll use this to make it a bit neat. So these all have. So considering this, we say this side is in tension. Then this side is stress. Then this is Fy over material strength. Consider this as our strain. Then this is under compression zone. Compression. So the features of this design curve are as follows. We consider the elastic modulus of steel reinforcement regardless of grade of the steel, so which we may assume as 200 kilonewton per millimeter square, which is the slope of the curve. So we'll put it here, it's supposed to be here, 200 kilonewton per millimeter square. The next one we'll consider is the yield strength or yield stress of a steel reinforcement, which is Fy, but for design purpose we divide it by the material strength, which is this. Then the third one is the stress after yield, which remain constant, which remain constant stress line. Then we consider it as 0.87. So here also y is given as Fy is 460 Newton per millimeter square.